Alright, so this is going to be interesting. I left my webcam at my office and there we go. So I'm having to use the laptop's webcam, which is oddly angled because right now the laptop's at about 30 degrees to me and it looks like it's actually lined up straight. Second is I'm also having to use an external microphone, so I'm not too sure what the audio sounds like on your end. On my end, the meters are pretty good. This is a really nice high. This is my personal boom mic, but I don't know what it picks up on the other side. The webcam's a lot nicer. Didn't receive any emails in advance for questions, so I do see there's a couple people waiting. If you have questions, go ahead and post it in the chat. Otherwise, I'm getting ready for my meeting at noon, so again, I'm here to answer any questions you have. Just type them up in the chat and I'll answer them as soon as I see them. question I asked how the Orgo 2 exams coming along. They fell into 2 piles, so I got them back. Damn it, this camera's really annoying. So got the exams back yesterday, graded them all, posted all the grades to the course website. They fell into 2 categories. There was a cluster at 80 and there was a cluster at 40. Don't know what to say. So the 80 to 90 group, I had 2 people that one got a 99, the other got a 94. Wake Tech doesn't curve, and even if we did, that 94 and that 91 really kind of make it hard to shift up an average, because I think the test average was a 58. We curved it up 12 points. That means 2 people just did better than 100, but we don't curve. The 40s and 50s, there were a lot of exams I saw where the responses were just left blank. Trying to think about how to address this with the Monday and Wednesday sections, but the thing is that a lot of the questions that got asked, you can point to the study guides and you can point to the notes and say that's where this was covered, that's where this was covered. So there was one where you took an alkene and you reacted with potassium permanganate, that creates the diol. I saw a lot of people that weren't even creating diols. I saw weird enols, carbon-carbon bond clipping. It was all over the place. The second step was you use chromic acid to oxidize this to a diketone. The diketone got weird answers for that when people were claiming it was clipping off the bromine. It was eliminating the double bond. They were getting epoxides for some reason, but none of that's in the notes. If you look at the notes, an alcohol oxidized is to a ketone. The last step was a Grignard reagent. That was the only challenging one, and I gave a hint saying that there's 2 products formed. There were a lot of exams where people just wrote 1 product, and again, the preceding 2 steps were incorrect. But that's usually the tip-off with these exams, is that if you look at the reaction and you say, well, we've never reacted with this particular functional group, you probably have an incorrect answer for your previous one. The synthesis problems, no one attempted the extra credit ones. The first one was honestly pretty hard. That would have been a solid 10 points if you had gotten it. You really have to go poke through the notes. There's one specific reaction that will do it, so I didn't expect him to do that. The second one, honestly, some people had some earnest attempts with the second synthesis, so that was 5 points extra credit. I like that one. It is a little nuanced how you do it, but definitely the last 2 were really straightforward. The odd one I kept seeing was people kept trying to do hydroboration oxidation. So there's one where you take an alkene and you convert it to a carboxylic acid with an alcohol. So you just form the diol and you oxidize it with chromic acid. So it's just a 2-step synthesis. And when the diol you form, one is a tertiary alcohol, the other is a terminal alcohol. The terminal alcohol oxidizes to the carboxylic acid, and the tertiary alcohol can't be oxidized. So 2 steps and you're done. People kept throwing hydroboration oxidation on this, and I didn't quite understand why, because you need the diol, and you had 2 options here. You had osmium tetrachloride, OSO4, and potassium permanganate at low temperatures, low concentrations. So you had 2 options on how to produce the diol. If you really wanted to go out of your way, you could have done the halohydrogen addition and then substituted off the alcohol. But in terms of what was covered in the notes, there were 2 ways to create the diol. And then you could have used chromic acid and probably a couple of others you could have used to actually convert it, but it was 2 steps. There was one where you had to form a bicyclic alcohol, and you start with a cyclic molecule that was a ketone. That was actually 1 step, technically 2, because you were supposed to do the protonation. I didn't take off points if people didn't do it with the acid workup. But that last synthesis was 1 step. You added, it was a terminal chloride. If you added lithium, it reacted with the ketone and it did a lot of internal reactions. So not quite sure what was going on with the last 70 points. Now, the first question there was, it was supposed to be triglycerol it was being asked for, 1,2,3 propane triol. I didn't take off any points for that one. There's a big red X through it. I just gave you full marks for it. That was actually, you saw the answers to the other version of that exam, so I didn't count how many points. One of the more concerning ones I saw, there were polycyclic, so there were these, it was asking you which of these can be converted to an epoxide. And it was 4 fused cyclohexane rings, each with OH groups in different positions. This was a discussion board question. Same discussion board question that said, okay, which of these can and can't be converted into an epoxide, and the one that can't be converted into epoxide, how would you make it? If you look at them, then there was only one that had trans geminal alcohols. So it was literally a discussion board question just with different molecules. A lot of people missed that question. They circled the one where the alcohols were cis to each other, and I didn't quite understand that because there was a discussion board that literally went over that concept. So I guess Wednesday and Monday, this is going to be a discussion we need to have to start a lab, particularly Wednesday because lab this week is very short, to say, I don't know what happened on this exam, but there were some of you who really solidly got it, and a lot of the people I saw in the 80, 90 range, points were lost for like little things. So they ran a reaction, but they like forgot an acid workup, or particularly there was one where they drew the correct stereochemistry. So there was one where you had to draw, you got a diol and you had to name it, and they drew it right, but they forgot to add the cis and trans to the name, or they had the cis trans in the name, but they forgot to draw on the stereochemistry. That's little points, and you clearly understood it, you just missed the little details. But it's the 40 to 50 range I'm really concerned about, because that 40 to 50 range, like, a lot of those exams were blank. People just didn't know what to do. So my concern moving forward for the Organic 2 folks is that the next test, which is on aldehydes, ketones, these intermolecular reactions, the ones where the molecule reacts with itself, this is a very common thing with ketones. We're going to talk about keto-enol tautomerization. This is a huge concept. So let me get my magic markers. And thanks to Alex for getting these for me. So we're going to start with talking about a very simple example here, which is this cyclopentanone. What will happen under acidic or basic conditions, and we're going to draw this as resonance, but it's not really what's happening. Is that we're going to bounce between the alcohol and the ketone, and the intermediate here is a lone pair on the carbon. So typically this is a lot easier to do with hydroxides, but you can definitely do this with H pluses. And because we can form this anion can attack the ketone. This is where we're going to get alpha beta unsaturated ketones. So this is an aldol condensation. This is going to be a huge chunk of the next unit because they do these types of reactions. So this will give rise to the microreaction, the Robinson annulation, the decarboxylation reactions. So if you're not understanding intermolecular reactions, so reaction with a molecule with itself, this next unit is going to be incredibly hard. And it's kind of build on what we did with the organometallics. So the organometallics, typically we're creating this carbanion. We're creating a negative ion, negatively charged carbon with a lone pair that's going to act as a Lewis base. And it's going to act as a Lewis base on a carbonyl, and aldehydes and ketones, these are carbonyls. So again, no one has necessarily failed out of the course at this point. There are a lot of people that have just dropped down to the DC range, and I don't think they're going to be able to come back out of it. The other thing is I think a lot of people are kind of feeling overly confident because, and again, this is speculation. I want to hear in person from students what happened on this exam. But the thing to keep in mind is that right now your Organic 2 grade looks really high, and it's not that high. And there's a lot of reasons why it's not really that high. So if you think about coming out of test 1, you only had 2 grades in the test book. You only had 2 grades in the grade book. And so you had test 1 and the lab. And in the course, this is 12% and this is 25%. So crudely in Blackboard, this looked like 33% and this looks like 67%. On top of that, the lab here was mostly lab worksheets. The lab worksheets are 20%, and you didn't have any lab reports. So the lab worksheets are super trivial. Usually you should be scoring better than 80s, if not consistently 90s and 100s on these. So you had 25% of the grade waiting for 67% of the grade, and that 25% was represented by the 20%, which really isn't representative of the hard parts of the course. Well, now you've got 12% due to the lab report. First lab report's been submitted, and if you didn't do well on that, the first lab report is now looking like, crudely, 35% of the grade, and this is looking like 65% of the grade. So the lab grades have now dropped, and they're going to drop by nature of just the lab reports are a lot harder to get good grades on. That's why they count for more. Now you also have test 2 under your belt. And these are starting to look more like 25, 25, and 50%. So as the semester goes on, these tests are going to start weighing more and more and more. They're going to catch up to that 48% of the course, and this lab grade is going to start counting for less and less and less because it's going to get closer and closer to the actual 25%. Again, Blackboard is treating this like 25, 25, 50. That's not how it works. It's really 12, 12, 25, but you don't have test 3, you don't have test 4, you don't have the final, you don't have the homework. Your lab grade's the same way. It's counting it like it's 20, 12.5, which is roughly 65, 35 for these splits. You've got another lab report, you've got your lab notebook, you've got your lab practical, you've got quiz grades in there. There are things that are not showing up, and so if you didn't do well on test 1, but you got that like near perfect score in the lab because you've just done the lab worksheets, you look like you got a solid B, if not an A in the course. But now that this lab is beginning to count less and less in the grade book, not the course, but just in the grade book, I think the grades are getting more and more accurate. So again, I want to meet with students and have students in person Wednesday and Monday, but my concern here is that I really can take this test and I can look at those study packets and I can point to where this concept was covered. And synthesis is a big part of this, and that's why there's 3 types of syntheses. The first one is synthesize and name. The synthesize and name, people did better on that, but again, I have people giving me like really weird things. It's like, if you can't name it, it's probably not the right product. I mean, the name and so the synthesis and name are the inherently easier problems because I can't give you something really esoteric and weird. It has to be something that you can name, and so these are generally much more straightforward, simple reactions. But I had people that were claiming that, I think it was first one I think was the dehydration. People were getting some really weird answers, like they were claiming sulfuric acid will convert cyclohexanol to cyclohexane. It's like, that's not how that works. It's really hard to actually recover an alkane after you functionify. Go through the naming of carboxylic acids. Yes, so carboxylic acids, this is going to be another one that we're going to state to really simple examples of. You can quickly trench into complicated space with these. Go through the naming of carboxylic acids. So again, let me bring up the slides and make sure I'm not telling this to you wrong. It's mostly I need the slides for the more complicated carboxylic acids. So with all these carboxylic acids, we're going to have the parent chain. And we're going to have, we're going to stick to more simplified answers. We have the parent name, and we're going to drop the NE ending and add oic plus acid. Now, with the, so something like if we had, something like this. 5. This is pentanoic acid. Sorry. We're going to drop the E at the end. So for a parent alkane chain, we end up dropping the E here. And we have oic. Ooh, I also need to remember that I can't, camera is different here. Okay. Dropping the E, we're adding the oic and acid. We don't have to specify the position because the carboxylic acid is going to take the priority, and because it's like an aldehyde, with the aldehyde you never had to specify where the aldehyde is because we know it's on the end of the chain. The same thing's true of the carboxylic acid. We don't have to specify a position because it has to be on the end of the chain. This is going to be a lot like the substituted naming for ethers. We are not going to get into overly complicated examples of this. 2 big reasons. One, it's easy to wade into overly complicated territory with these. The most we're going to see are maybe 1 or 2 functional groups. And when I say functional groups, I'm leaving off alkyl halides. those are named just like alkane branches. But things like, we're not going to have like if we're going to have a ketone or an aldehyde on there, we're not going to have like 30 or 40 functional groups. We're going to have pretty straightforward things. The second is just that in practice, most carboxylic acids we work with fall into two categories. Common ones, and the common ones are things like pentanoic acid. They're very straightforward. The second are ones that are actually named differently because they fall under a different category. So, amino acids. Amino acids contain carboxylic groups and amine functionalities. We don't name them like this. We name them by because they're biomolecules, we name them as biomolecules. So, alanine, like all the different little peptides. So, we're going to inherently keep it simple because there is no need to learn the really super complicated carboxylic acids. Probably they're going to fall under biomolecules, and that's where we're going to see them again when we get to the end of the semester with triglycerides and saponification. Basically, carboxylic acids, the ones we use most are very simple, and the complicated ones are probably biomolecules, which are not going to fall underneath IUPAC naming. They're going to fall under biological, or they're going to fall under biochemistry naming schemes. But mostly this, take the parent team, drop the E, it becomes oic acid. If we have a diacid, we're not going to play the weird thing where like the parent chain doesn't contain both acids. There's probably a way to name that. I haven't found it. But if we're looking at dicarboxylic acids, the worst will be like cyclic ones because those are pretty easy to name. But, oh yeah, that's what these office hours are for. Like if you need someone to talk to you through it, we also have the Friday office hours as well. Again, I kind of want to keep this, so what I tell students, the nice thing about organic too is the molecules get so complicated that we inherently have to keep the naming simple. This is going to be true pretty much through the rest of the semester. In fact, when we talk about, you'll see this with the aldol condensations. The aldol condensations actually end up creating usually 2 to 4 chiral centers. And so for you to name the product of an aldol condensation, you're going to have cis trans, RS, and then all the other naming rules show up on top of it. We're pretty much going to skip naming beyond simple compounds. And the notes even say this, that if you look at, explain slide 3, if you look at what's formed, it's super complicated. Okay, so when we look at intermolecular forces, so we look at intermolecular forces and how molecules interact. Broadly, there are 3 categories that for strength of interaction that occur with organic molecules. Dispersion forces, this is what your alkanes interact with. Basically, alkanes are nonpolar. The only way to get them to interact is through what's called an induced dipole. So basically, for a moment, the electron density shifts to one side. This causes it to happen in other molecules. These are very weak intermolecular forces, which is why if you look at something like hexanes, hexane weighs 84 AMUs. For something that weighs 84 AMUs, it boils at like room temperature, whereas water, which only weighs 18 AMUs, just oxygen and hydrogen, doesn't boil to 100 degrees C. So alkanes have incredibly weak intermolecular forces. Next up is dipole-dipole. Dipole-dipole is better, but it is not the best in terms of making molecules stick together. What happens with dipole-dipole is that we have a charge buildup due to electronegativity differences between 2 elements. So if we look at the carbonyl carbon and its oxygen, the oxygen is negative, the carbonyl itself is positive. Now, that said, while it is stronger than alkane interactions that just induce dipole, London dispersion force, it's still not the best. Ketones are still pretty volatile. Acetone is a great example of this. So if we look at something like acetone, this is a ketone. Let's see, 36. 52, 58 AMUs crudely. Acetone readily evaporates. If you pour it on the bench and wipe it, it will clean itself off in a few minutes, less than that. Water, again, weighs 18 AMUs and it boils pretty solidly at room temperature. But when they do interact through their dipoles. It's just that these are not particular. While these are polar bonds, these are not strong interactions. Carboxylic acids engage in hydrogen bonding. So what will happen is that they will exchange hydrogens with each other. And because of this, it acts like an ionic bond. So if we look at something like, what's that acid that ants use? Acetic acid. So if we look at something like acetic acid, it's not what ants use, but acetic acid is one of the simplest acids. This is in vinegar. That's what makes vinegar vinegar. Acetic acid doesn't boil to like 70, 80 degrees C. So with this hydrogen bond interaction, we actually get really, really good bonding. And that's more what that slide is trying to get across to you, is that if we look at aldehydes and ketones, they are better at sticking to each other than plain alkanes. But carboxylic acids are definitely going to win in terms of who has the stronger intermolecular forces. Yes. So when we look at question just got asked about using lithium aluminum hydride versus sodium borohydride, and so this is a carpenter's hammer. Let me give you a good analogy. Hold on, I'm right next to my workbench. So in carpentry, there are several different types of hammers you use depending on the job you're using. So this is what's considered a finish hammer or carpenter's hammer. Or not a carpenter's hammer, it's a finish hammer or tack hammer. So weighs about roughly 8 ounces, very small head, a very small claw on it. This is designed for finish work. So if you're doing some type of like trim work or something that people will see the end result, this is what you want to use. Now, you really can't beat in like huge nails with this, but it's really good for little nails because even if you hit the wood, it doesn't leave a really big like bruise in the wood. This is a rough hammer. And so there's your finish hammer, there's your rough hammer. Your rough hammer here, this is a 1 pound hammer. Beyond this is, I don't have one on hand, is a maul or larger hammer. This you would never use for finish work because if you hit the finish, you're going to tint up the finish really bad. But if you want to drive in like decking nails, which are about 2 to 3 inches long, this is what you'd rather use. So this has a lot more force, but it's also not very controllable. This has a lot of control, but doesn't have a lot of force backing it up. That's kind of the difference between these two. So this is kind of your finishing hammer. It's very small. It can only do basically reduction of aldehydes to alcohols, and ketones to alcohols are going to be the most use we find for sodium borohydride. So we're basically making alcohols, and we're going to focus on ketones and aldehydes. But the nice thing is it really can't do anything else. So let's say you have other sensitive functional groups on the molecule like a carboxylic acid. The nice thing about this is that it won't reduce those down. The drawback is that it also tends to be a little more slower. Now, you can see this relative stability because you worked with sodium borohydride in the lab this week. So it's actually air stable. It won't decompose in the presence of air. Lithium aluminum hydride is not the same way. This will actually decompose in the presence of air. And not only will it reduce ketones and aldehydes, it'll do carboxylic acids, esters. It will reduce pretty much anything that contains an oxygen-carbon double bond. And so this sucker here will basically break apart any functional group that can be reduced. The trade-off here is that while it can do it, it's going to do it to every single functional group. So it's powerful enough to reduce off your carboxylic acids and convert everything to an alcohol, but it's not gentle enough to selectively do it. So this is the preference between the two. Now, again, we're not going to kind of like a more graduate level course is going to focus on you switching, being judicious in which one you use. So if you were to take something like Organic 3, which is a course you have to take if you were going to be a chemist, if you're going to go on for graduate school in chemistry, you would tend to focus more on like situations while you would use one over the other. We'll also talk about what ketones are considered protecting groups. So let's say you wanted to let's say you had this molecule here. So 2-oxopentanoic acid. And you want to convert this to this molecule. So you want to replace the carboxylic acid with an alcohol. Now, if you use lithium aluminum hydride is the only thing that's powerful enough to pull off that carboxylic acid, but it's going to pull off the ketone in the same breath. If you try to convert them both to alcohols, you're going to have a lot of trouble selectively oxidizing it back. So let's say you did lithium aluminum hydride. You would get this. There is a way to do this, what's called a Fetazone oxidation. Fetazone oxidation is selected for secondary alcohols first, followed by tertiary, and even the tertiaries it'll convert to aldehydes before it does carboxylic acids, but it's a bit more challenging of a synthesis. The other option is we can use a protecting group. So if you use ethylene glycol, we end up forming this group. Oh, I know you can't see that because of the light. Seriously? So you actually end up getting this diether down here at the bottom. And yes, I'll turn it back around so you can see it. But you form this diether, then you can do the lithium aluminum hydride, and then you deprotect with an acid, and this will get you back to this compound. So there are ways of doing this, but again, this is kind of more of what a graduate course would focus on, is protecting and deprotecting groups and these different kind of like nuanced oxidations to achieve what you want to achieve. So we're going to kind of keep it simple. Most examples, you can use sodium borohydride and lithium aluminum hydride interchangeably. The reason why the notes are going to go so in depth into this is because we are trying to set you up for success if you decide to go on for a chemistry degree. We do have a few people that are looking to go on to like PhD in chemistry or at least a master's in chemistry. And so this is good foundation for them. But we also recognize a lot of you are going on to med school, nursing school, PA school. You don't need to kind of like worry about the depth and nuances with this. Again, this is organic too. We're providing you with an introduction to this. Mastery would be kind of a junior senior level graduate course. But again, this is good information. No, lithium aluminum hydride is this nice, soft reducing method. Lithium aluminum hydride is a sledgehammer, and it will reduce everything it gets its hands on. That's the trade-off. I also kind of wondered about calcium hydride. It's something I've kind of wanted to look up. I used to work with calcium hydride as a drying agent, so CaH2, and we would put it into whatever water-free, air-free solvents we were working with because it would react away the water to form hydrogen and calcium hydroxide, which was insoluble in the organic phase. I've never looked up to see if it can be used for these types of reactions, mostly because it would be more of an interest question than an actual practical question. I bring it up because we used to store this stuff out in the air, and UC Santa Barbara was like right by the coast, so we definitely had humidity. And I always kind of wondered why we never stored it dry, like why we didn't store it in nitrogen or argon boxes. And it was kind of weird to me because when I finally got to buy a new bottle of it and open it up, it looked nothing like the old stuff we had sitting out on the counter. So I seriously wondered how much of what we threw into our organic solvents was really just calcium hydroxide that wasn't really calcium hydride anymore. Yes, so the bigger thing is just understanding what they can be used for. Again, look for the packets, and the packets are going to kind of show you the depth to which we're going to apply this information. But you're going to find, I'm not going to give you examples where it's like, you have to make a choice in terms of like, are you reducing, you should be able to do a lot of these reductions in a single step. So if you want to reduce a ketone over a carboxylic acid. So let me give you an example of the fair problem. So if I asked you to reduce this to this, you should be able to answer this as sodium borohydride because it can be done in a single step, and you should know that lithium aluminum hydride would be too aggressive for this. Yes, you do need to worry about stereochemistry to the extent that you will get an equal mixture of both the R and the S. So this will end up being a chiral alcohol when we get done. You'll see both the R and the S. If it is needed, it will be asked for. Generally speaking, I will probably not ask for the stereochemistry because, as we're going to find out with aldol condensations, it just gets too daunting to draw out every step, and so we just imply that, yes, there are more out there. But you may see questions like multiple choice questions that tell you to specify like, okay, which of the following would not be formed? Now, I could ask you to make this molecule. That would be fair because you can do this with lithium aluminum hydroxide. So a situation where we need to use a soft touch versus a hard touch. But to ask you something like this, I think would be too much. Because in both cases, you're going to need lithium aluminum hydride, but the question is whether you deprotect or how you back oxidize. That's too hard of a question. Again, when I say like you're keeping stereochemistry in mind, like we're going to keep it reasonable because again, we're getting into molecules where the number of chiral centers. So when you took Orgo 1, generally we had one chiral center and we manipulated the chiral center. And then we kind of got the two chiral centers with the alkenes and we manipulated the chiral centers. Now we're potentially getting 3 and 4 chiral centers, and so you get 2 to the 4 combinations, so there's 8 molecules you'd have to draw out when you got done. That's really way too much. Like, honestly, when you get down to it, that's just too intimate of a level of detail for these types of molecules. Why go to that nauseating length of detail when you understand the overall reaction? Again, organic 1 and 2 are meant for majors, but they're also meant for non-chemistry majors as well. If you truly and honestly want to go to a course that will worry itself with this level of detail, Organic 3 is the place to go. And Organic 3 will begin to worry about, we really want to control these chiral centers, we really want to control what we're making, because the idea is that if you're going on for Organic 3, you're a chemistry major. You're probably going to be a bench chemist, and you need to know how to do these types of things. You'll see these with graduate courses. Graduate courses will definitely go into this type of depth. But it's presupposed that you're going to be a chemistry major. We want you to be aware of this. Like, don't just blindly memorize the information. There is still stereochemistry involved. But to the same extent, you're not chemistry majors. And teaching you to such an, I'm going to say absurd, I know that's not the right word. Teaching you to this depth of theory is not necessarily productive. Because at the end of the day, it's like learning a foreign language for the sake of just learning the foreign language and never speaking it again. We just kind of want to pick you up, give you kind of the big picture of what's going on, and then if you go on to be a chemistry major, making sure that you're on good footing, that you can't sit back and say, well, we never learned this, or they never taught it to us right. We taught it to you, it's just that we didn't really emphasize it that much, because at this level, it's too much. It's way too much information to be trying to comprehend. So again, like with these 3, I'm not even bothering with the stereochemistry. Most books don't bother with the stereochemistry. It's implied that it goes both ways, and we're going to kind of leave it off because that's not really the big picture. A junior level organic course or graduate level organic course is going to focus a lot more on these details, because the assumption is you're going into that field at that point, and you do need to worry about these types of details. Because genuinely, if we absolutely hated you, like absolutely hated you as students, we could do that to you and make you draw every single combination. So you create 3 chiral centers here. You're going to have the R's and the S's. And the thing is that some of these are meso. So you would need to not only recognize that there are 3 chiral centers and potentially 2, 4, 8 different molecules that can be built. Some of these are chiral. And because some of these are chiral, you're going to end up having to eliminate the ones that are actually already, that are meso with themselves. So they're already mirror images of themselves. So something like this would be a nightmare to answer on an exam accurately, because you'd have to basically brute force your way through all 8 combinations and figure out which ones were redundant. We're not going to do that to you. So something like this would be fair game. And when you get done with this, this isn't even a chiral molecule. When you get done making it, it's cyclohexanol. Cyclohexanol doesn't have any chiral centers, so you can just write OH just fine. That's fair game. But yeah, something crazy chiral, not going to happen. Now, if this is the test I'm thinking of, let me bring up the packets just to be sure. There's a decarboxylation reaction. Yeah. These get fun. Yeah, you can even see in the synthesis problems in the packets, it's not even bothering listing the stereochemistry. You could never keep track of it. So the one on page 21, there is no way you could keep track of that. respond to a few more messages I'm getting. And again, I've got the chat menu up if you've got any questions. All right, just got a question under lab resources tab. There are questions posted for each lab. Do we need to answer those post lab? You just need to answer what's in the lab manual, and anything that's on the lab worksheets. This is, so the course we use, there's a shared shell that we use for the organic curriculum, for Organic 1 and Organic 2. I try to clip out all the stuff I don't use, but every now and then the stuff just kind of slips through the cracks. We do there is a master shell that contains all the organic curriculum in it. Sometime, one of our instructors really prefers to do pre-lab, post-lab quizzes. That's why that material is there. I don't use it, but again, sometimes I don't catch all of it. But yeah, in terms of like what you're required to do for post-lab, you only need to do what's in the lab manual and what's in the lab worksheets. All right, if there's no more questions, I have a meeting at 12 o'clock, so I'm going to head out. Again, if you have questions, please feel free to email in advance. These are not lectures, these are not lessons, these are office hours, so I'm here to answer any questions you have. And I will see several of you tomorrow.